Hello, my name is Richard Marcus and I will present TGView3D to you. It is a system which is capable of visualizing theory graphs in 3D. But first, what are theory graphs? Well, they're exactly the visualization of OMDoc MMT formalizations, and this way they are capable of presenting complex knowledge structures. If we look at this theory graph here, it was handcrafted by a person. We can see that this is already a considerable amount of work to do something like this. And moving to bigger theory graphs, it becomes impossible to do this. Here, for example, we can see the math in the middle archive. And while this visualization is still somewhat clear, moving to even bigger libraries, and as we have seen in this conference, libraries are always getting bigger and bigger. So visualizations like this quickly become unusable in practice. Then we also have 3D visualizations, for example, for Isabel. And while we can see clusters in this visualization, it becomes not so usable for theory graphs. To see why, we need to look closer at the structure. We have theories as nodes and theory morphisms between theories. The most important ones are inclusions, which are responsible for representing inheritance relations, and views for other relation between nodes. Their exact meaning is not so important for this presentation. We really need to view them from the graph perspective. So we have a directed acyclic graphs from inclusions, and simply other directed edges which may introduce cycles in form of the views. Then we have also a tree structure that we can find within the libraries in the form of MMT namespaces. And the reason why this 3D visualization we saw before doesn't work so well for theory graphs is that here we need to represent the inheritance hierarchy in the visualization like we have seen in the graph with visualizations. However, there is no single tool that can handle graphs that use a combination of these different types of edges. So the solution is TGView3D. We get the graph files in form of JSONs, which are directly generated by MMT, and take care of the layout and rendering. And for framework, we use the Unity game engine, which allows us to build a web version and also executables for many different platforms. So if we want to look at the choices we have for a 3D layout algorithm, we first can look at the force-directed layout. There we have attractive forces between connected nodes on the one side, and a repulsive force between all nodes are there. If we apply these forces iteratively, we will be able to minimize system energy and get an organic layout like this. This is Latin theory graph, and this is already a rendering from TGView, showing only the namespace structure of the Latin library. Moving to 3D, we see better distribution, but not really a semantic difference yet. If we look at layers, like in the graph with visualizations, we can first compute this layering only, and then use forces to distribute the nodes within the layers, and arrive at visualizations like this. And visualizing them in 3D already helps here. But we still have a big problem that these layers are rather constraining. So we want to use a local hierarchy instead. This means that successor nodes are always following and predecessor nodes are always before a node, so that the inheritance relations are correct. And we can implement this by introducing hierarchical forces, which work identical to the repulsive force in a regular force-based algorithm, but are of course only applied to nodes with hierarchical relations. Then successors repel node downwards and predecessors repel node upwards. Then we get a layout like this, which is way more compact compared to the layer-based layout that stretched the graph really wide. If you now think back to our original thought that we want to have multiple edge types, we see that they are really problematic in such a 2D layout. Even if we would order the nodes better within the layers, view edges, the blue ones, within a single layer are simply not visible at all. Taking our hierarchical forces already makes this better. And in 3D, we can really see them well if we look at the top of the graph. Looking at the full graph with all edge types activated, you can see that while we can integrate them all into a layout, even in 3D, it is still a bit cluttered. So we need better graph interactions. In 2018, we tried to do this in VR, to have more screen space and better interaction possibilities than just mouse and keyboard. For example, grabbing nodes with hands, or just simply turning the graph with your hands. But we had a few practical problems. Not everyone had access to VR hardware. It was difficult to integrate into usual workflows. And in the end, it only shifted the problem, and we were in the same situations, just with a bit bigger graphs. So we developed very different filtering methods and even possibilities to directly edit the graph. Here are a few filtering methods we will now see in detail. And the biggest opportunity here is to simply deactivate edge types, because we're not really using them at the same time, so that we can here, for example, see views only, or on the other hand, have only the includes visible, and freely change this from within the graph view. Then we also have scaling, and what this really does is changing the node spacing so that we can really get into those dense clusters. Then we have 3D slicing to explore the graph. We simply hide what is in the distance and then move through the graph, so we only see one slice of it at a time to reduce the amount of complexity in the graph. Another possibility is to crawl through the graph via node selection, so that if I have an interesting node, I can just follow its nodes and edges through the graph. Then we are doing something that we call hierarchical clustering. This is different to the methods before, and this actually changes the graph. We collapse nodes into their namespace clusters, and this way reduce the graph complexity. This can be repeated until we arrive at a really simple presentation of the graph. And here we do something we call edge propagation. That means that we collect the edges from the original nodes into the new clusters, and this way we can still see how the different nodes within the namespaces relate to each other. So until now we only operated on the theory level and with their relations. With the MathHub integration we can now do something better. Just press a button, we can jump into the TGView visualizations and even request other libraries from MMT. Then we can jump into the theories in TGView and load a special representation that shows what is inside a theory. So we can now visualize theory graphs efficiently. We have the hierarchy-based forces and can now also handle the different types of edges. And finally, allow the user to customize within the graph viewer. This way, he can create presentations to show his work to other people. Users can explore what is inside the libraries and even use it for debugging. Then we have the system interaction, which right now is only the MathHub MT integration, but we want to do something better in the future. For example, we want to have really specialized builds that work closely together with other tools like maybe theory improvers or something like that. And on the other hand, build a graph ecosystem that helps us to import very different kind of graphs. Last, I want to give you a quick preview of what we have in the pipeline. Better visualization of theory improver libraries, model pathway diagrams, argumentation frameworks, and drafts that we built from our lecture notes. And we also have not forgotten virtual reality, especially with augmented reality. We think there will be interesting opportunities for the future. Thank you for your attention.